we are discussing passive network synthesis. As we said in the previous session, where we discussed about Hybris polynomial and positive real functions. So, coming to the Hybris polynomial, the necessary condition is that when we have a continued fraction expansion, the quotient which is derived from that continued fraction expansion has to be real and positive. So if it encounters a negative quotient, then it is not a Hybris polynomial. And we have also seen positive real functions, which say when we have a positive real function, a function should be said to be positive real function if all the poles and zeros should lie on the left side of the imaginary axis or the S-plane, and second condition, if any simplex roots lying on the j omega axis, the residue of that should be real and positive. No, should not be having any imaginary or negative terms. So if it is having any negative terms or imaginary residue, then it is not a positive real function. The third necessary condition is that real part of, that is real part of f of the function has to be greater than or equal to 0 for given real function of s greater than or equal to 0. So let's take two more problems in which we will see whether they are positive real functions or not. Okay. So why we need to know the positive real functions or not? Given any impedance function or admittance function, we need to realize a network. That's our main target, synthesis of passive network. Okay. So let's go further for deriving or knowing whether positive real functions or not. Let's take this problem. F of s is equal to s into s plus 3 into s plus 5 divided by s plus 1 into s plus 4. Test whether this function is positive real function or not. So as we said, the first test we are going to do is we will see whether poles and zeros lying on the left side of S plane or not. So from this f of s, given f of s, we will see where are our zeros. Zeros are 0, minus 3, minus 5. The poles lies at minus 1 and minus 4. So if I plot this at S plane, all this lies on the left side of so at 3 we have 0, at 0 we at origin we have 0, at minus 5 we have 0, whereas poles lies at minus 1 and 4. Poles lies at minus 1 and minus 4, minus 1 and minus 4. So if you see, all of which the roots lies on the left side of S plane, so the first condition is satisfied. The second, we will see whether the residue of that is positive or real or not. So as there is no root lying on the j omega axis, the second step should not be carried out. So can be skipped, second step, as there are no residue lying or there are no roots lying on the j omega axis. Third one, the third state is that real part of f of j omega has to be greater than or equal to 0 for omega greater than or equal to 0. So for this, as we said in the previous class, we need to find out the numerator polynomial having odd and even parts and denominator polynomial having odd and even parts. And the necessary condition is that m1 of s into m2 of s minus n1 of s into n2 of s is greater than or equal to 0. So this is important to find out. So I will expand this. So we will have s cube plus 8s square plus 15s. S cube plus 8 square plus 15s divided by s square plus 4s plus 5s plus 4. Right? So from this we will find out the positive polynomial, the even polynomials or the odd polynomials. So m1 from this, So the m1 is the even part, that is 8s square, and the odd from the numerator polynomial. So n1 is s cube plus 15s. From the denominator polynomial we will have m2. m2 is what? S square, the even part of the polynomial, s square plus 4, and n2, the odd part, is 5s. So we need to do m1 m2 minus n1 n2. So if we do that, so it will end up with 8s square plus 4 minus 5s s cube plus 15s. Okay, should be greater than or equal to 0. So if we expand this, 8 to the power s to the power 4, 32s square, 5s to the power 4, 75s square, should be greater than or equal to 0. So once we do this, we will find out the s to the power 4 term and s to the power 2 term. So 3s to the power 4 minus or plus minus 43 minus 43s square should be greater than or equal to 0. So next term is that this is the real part of this. m1 m2 minus n1 n2 greater than or equal to 0 is the real part of f of s. So denominator of that is real. So only this is necessary condition which we have to test for polynomial having higher orders. So when I keep s is equal to j omega, this equation leads to 3 into s j omega to the power 4 leads to 3 into omega to the power 4. J to the power 4 is positive 1. So minus 43 times of s to the power square. So j omega square leads to minus omega square. Should be greater than or equal to 0. Minus minus become plus. So we have end up with 3 4 to the power 4 minus 43 plus 43 omega square should be greater than or equal to, and hence it's true that 3 omega to the power 4 plus 43 omega square will be always greater than 0 for any value omega greater than 0. So hence my function, which is f of s, is a PR function. Okay. So the one which we have given, which is under test, the f of s into s plus 3 is into s plus 5 by s plus 1 into s plus 4 will lead to a positive real function. Okay. Let's see. Let us take one more problem where which we will know whether the function leads to a positive real functions or not. Consider y of s. Y of s is equal to s square plus 2s plus 20 divided by s plus 10. Let us test this function y of s. As we said, f of s can be a z of s, which is the impedance function, as well as it can be y of s, which is admittance function. So let us test whether this y of s is positive real or not. So as we say, the first and foremost step we have to do is whether the roots, that is poles and zeros, lying on the left side of the s plane or not. So if I want to find out from this, let us write s plus 1 whole square plus 19 divided by s plus 10, right? So we have the poles j root 19, s plus 1 plus j root 19. So divided by s plus 10, correct? So we have the zeros which are lying at minus 1 plus j root 19, and another is lying at minus 1 plus, minus 1 minus j root 19. Whereas my poles lies at s is equal to minus 10. Correct? So if I plot from j omega, sigma into j omega, so my one pole lies at s is equal to minus 10, and my zeros lying at minus 1 plus root j. Somewhere, consider this is j root 19, and this is somewhere j root minus j root 19. So somewhere here, from it is 1, then let's consider this will be my 2 zeros line. So obviously they are on the left side of this plane, so first test is pass. The second one, are there any simplex root lying on the j omega axis? No, there are no roots lying on the j omega axis. Hence, this need not to be carried out. The residue test may not be carried out. The third one, we have to find out whether the real part of f of y of j omega, whether it is greater than or equal to 0 or not, for omega greater than or equal to 0. So m1 m2 minus n1 n2 are greater than or equal to 0 or not. m1 of s, m2 of s, n1 of s, n2 of s. So from this, can you be able to find out what is m1? m1 is given as the even part of the polynomial, the numerator polynomial, that is s square plus 20. And what is the odd part of the numerator polynomial? It is 2s. Correct. So the m2 is even part of the denominator polynomial, which is nothing but 10 itself. S to the power 0. n2 is having only s term. So we need to put into m1 into m2 minus m1 into n2 in order to find out whether real part of this is greater than or equal to 0 or not. So we end up with 10 s square plus 200 minus 2 s square, right? 2 s square, which is equal to greater than 0 or not. So we have 8 s square plus 200 is equal to or equal to 0. Keeping s is equal to j omega, we end up with minus 8 omega square plus 200 greater than or equal to 0 or not. So is it for greater than 0, is my omega, this real part of this is real part of y of j omega, is it greater than 0? That is minus 8 omega square plus 200, is it greater than or equal to 0? Maybe for omega is equal to 0 it is true, but as we go omega greater than 5, omega greater than 5, this will lead to a negative value. Correct? Minus 8 into 25 is 200, it leads to 0. Omega greater than 5, this leads to a negative value. So hence, the given function is not a PR. Not a PR. Correct? So, if a function is of which is not a PR function, we cannot be able to realize a network. So, having an assumption telling that a given function is a PR, we will go ahead with realizing a network. Okay, so the next, whichever I am going to take up the example, will be a PR function. Okay, so from that we can able to realize a network. Fine. So let's go further. Yes, coming to the synthesis of a network function. So as we said, synthesis is nothing but realization of a network from a given characteristic equation or excitation and response. Given an excitation and response, you have to realize a network. And there are many ways in which you can able to realize. One is Foster form of realization, that is form 1 and 2. There is a Carr form of realization, that is form 1 and 2. Let us consider a given function is z of s. Okay, which is nothing but, let me take any polynomial which has got numerator and denominator. Let me take a general, yes, an s to the power n, an minus 1 s to the power n minus 1, so on till a naught. And let me take denominator bm s to the power m, bm minus 1 s to the power m minus 1, so on till b1s plus b0. Okay. So given this function, we need to realize a network. We need to realize a network from this given function. It can be of any order. So the order states that if it is s to the power 4, there will be 4 elements. S to the power 3, 3 elements will be there. So this can be again expand. That is partial fraction expansion you can do, or continued fraction expansion you can do. So it may result like Same thing, if I want to remove the higher order polynomial, if consider numerator is having 1 degree greater than that of the denominator, as we seen in the previous Hybris polynomial, that is continued fraction expansion, it will end up like this k times of s plus something something, right? If I want to remove 1s from the numerator. So the ks is nothing but my z1 of s, and the rest can be nothing but z2 of s. We can expand this, the first function and the rest z2 of s. z1 of s is removal of the first function, that is an s to the power n divided by bm s to the power m. Okay. If I want to take the difference between the numerator and denominator polynomial is 1 order. Okay. Then bottom we will have s to the power n minus 1, bn minus 1, s to the power n minus 1, that way. Okay. So let me take that only. Okay. So I will just remove this. So this is bn minus 1 s to the power n minus 1, bn minus 2 s to the power n minus 2. So it goes on. So numerator and denominator having a difference, n minus m is 1. Right. So we can find out z1 from this equation and the rest will be z2. Like z1 will be this divided by this will leads to an by bn minus 1 times of s plus the rest will be an minus 1 dash s to the power n minus 1 plus so on till a naught dash divided by in denominator will remain as it is bn minus 1 s to the power n minus 1 plus bn minus 2 s to the power n minus 2, so on. Okay. So from this we found out that this is z1 of s and this is z2 of s. This is continued fraction expansion which we have seen in the Hybris polynomial. So from this we can understand this z1 of s can be represented as series element, correct? z1 of s, from observation it should be an inductor L which is having L into s, that is an by bn minus 1 value, and the rest is your z2 of s. Rest is your z2 of s. Right. So given z of s can be represented as z1 of s plus z2 of s. z1 of s is in series with respect to z2 of s. z2 of s again can be expanded further into the other subcomponents. So they whether we will be in series or parallel we can see in some problems. Okay. So what it indicates is nothing but z2 of s. z2 of s is nothing but z of s minus z1 of s. We removed a pole from infinity, right? We removed a pole from infinity from z of s. Z of s having an order numerator will be having 1 degree greater than that of the denominator, and we just made such that now next will be denominator and numerator may be same or may not be same, but we removed one element. We removed this z1 of s is one pole from infinity. Okay. So there are many ways in which you can go further on realization. Here it indicates an inductor, so z is removed, replaced with an inductor. Then go further. We have to go continued fraction expansion or expansion, partial fraction expansion to know which other elements exist. Okay. So this method is nothing but removal of pole from infinity. So removal of pole from infinity. If you want to remove a pole from infinity, that means whenever the denominator polynomial has a degree 1 lesser than that of the numerator, there are n zeros which are of more number and poles are in lesser number compared to the numerator, right? Compared to the zeros. So one pole has to come from infinity and settle onto the 0. So, and the necessary condition is that the degree of numerator and denominator should not be greater than 1, because there should not be more than one pole lying on the infinity. It will impair the stability of the network, correct? So that's our necessary condition. So a network can be synthesized by removal of a pole from infinity. If we remove a pole from infinity, we remove one element, that is Z of S from Z2 of S. That is, if I say AN by, we know that resistance in Laplace is written as a resistance. Inductor can be written as, when in Laplace L is written as Ls, correct? Inductor with value Ls, if it is Z, impedance function. If it is admittance function, then CS. If first element is series element, then it is combination of parallel. You see in that removal of zeros, removal of pole from origin. So a capacitor is written as 1 by CS, correct? 1 by CS. So we removed an inductor and we replaced in series with the element. So we removed an inductor from this Z2 of S. Fine. So the next method in which you can find out or synthesize a network is by removal of pole from origin. Removal of pole from origin. What it indicates, given a function Z of S, let me reverse it and write A0 plus A1S, so on till AN S to the power N, divided by denominator B1S, B2S square, so on till BM S to the power M. Bn S to the power M. Why I wrote like this? Because we need to remove a pole from origin. Pole from origin. What indicates? Denominator will be having a degree maybe equal or greater than that of your numerator. So you can see yes can be taken out, and that yes is lying on the origin of S plane, right? So we need to remove that, then we can expand this, or we have to do conjugate fraction expansion, whatever the way you want to go further. We can write A0 by B1, right, times of S, right? A0 by B1 times of S, plus it can be again further written as A1 dash plus A2 dash S plus so on till An dash by S to the power N minus 1 divided by B1. S is taken out, right? B1 plus B2S plus so on till Bm S to the power M minus 1, right? So this will be the Z1 of S now, and this is Z2 of S. If you see Z2 of S, Z1 of S minus Z1, Z of S minus Z1 of S. So we removed a pole from origin from this Z2, right? So we removed that pole from origin. So what indicates Z1 of S is something like in the form of K by S plus Z2 of S. Z1 of S, K by S. When we can have K by S in Z form, when we have an impedance function, whenever there is a capacitor exist, then we can write 1 by Cs, right? So the capacitance value is 1 by K, which is nothing but B1 by A0, which is nothing but B1 by A0. Hence, I can replace this with the capacitor with the value B1 by A0 or 1 by K, and we can have Z2 of S. We can have Z2 of S, 1 by K farad. What if it is impedance function, admittance function? If this function straight away, this function is nothing but, instead of Z of S, we would have Y of S. Y of S is equal to Y1 of S plus Y2 of S, nothing but K by S plus Y2 of S. Then we would have had parallel. We would have had parallel inductor. That is 1 by K inductor, and this would have been Y2 of S. Right? 1 by LS is in parallel. Why? If it was, function was Y of S. If function was Y of S, that is Y1 of S plus Y2 of S. Given a function, if you want to remove. So what we understood from the previous removal of pole from infinity and removal of pole from origin, in removing a pole from infinity, we have to remove the higher order S terms. We have to remove the higher order S terms, right? We have to remove the higher order S terms. When we go for the removal of pole from origin, we need to remove the lower order S term. That is A0 by A0 term has to be removed. A0 by B1 times of S, 1 by S. So previous case we have an inductor. Here we had an inductor, then Z2 of S, right? Inductor with the value AN by AN minus 1 Henry. AN by BN minus 1. BN minus 1 Henry. So Z2 of S, go further. In any method we can derive. If it was Y of S, if this function was Y of S, then we would have had CS. So capacitor would have. If it was Y of S, then we would have had capacitor, then Y2 of S. What we understood from this, removal of a pole from infinity means we have to remove a pole from the equation. That means the inductor is in series with the other functions. If it was the admittance function, then its capacitor is in shunt with respect to the other elements. And removal of a pole from origin, nothing but we have to remove higher order denominator terms, nothing but we have to remove a capacitor from the series. If it was an admittance function, if the given function instead of Z of S we would have had admittance function, then nothing but an inductor in parallel with the reciprocal element. These are the two. Another there are two. One is removal of conjugate imaginary poles. So the last one is removal of constant. Removal of a constant. So third one is removal of conjugate imaginary poles. So here given an equation, that is whether it is a Z of S or Y of S, if it is in the form something in the numerator polynomial and denominator will be having S square plus omega square into some other polynomials multiply. So the function has to be positive real function, first condition. Then second, we want to write in this series form, that is Z1 of S plus Z2 plus that, so on, in order to get synthesize our network. So whenever there exists a conjugate imaginary poles, we can write this in the form K1 S plus J omega plus K1 star S minus J omega plus some Z2. Correct? It goes further. Maybe P of S by Q1 of S goes further. We have to find out the residue, that is K1 and K1 star. Once we find out the residue, that has to be real and positive. Real and positive means K1 is equal to K1 star. Correct? K1 is equal to K1 star. Let me take it some K only. So I can write K by S plus J omega plus K by S minus J omega. So I can write further, okay, this as S square plus omega square, right? But what happens to this numerator? K into S, 2ks. The other term is plus jk omega minus jk omega get cancelled. So we have this. Why we had this term? Just because we know that z of s is positive real function. In the positive real function, the conjugate, the residue of the simplex root, the roots are lying on the j omega axis, right? S minus j omega, s plus j omega. S is equal to minus j omega, s is equal to plus j omega, lying on the j omega axis. So the residue of that has to be found out. As we know that previously that this is a positive real function, then we can tell this is correct. So when we apply, we had this. So when we can write a z2 of s in terms of z of s minus this term, that means we removed a conjugate poles from the function equation. Removal of conjugate imaginary poles. We removed this from z of s in order to get z2 of s. Right? So what are these functions? So as we see, it has to be z1 of s and z2 of s. Right? It has to be z1 of s in series with z2 of s. So z1 of s is this term. What it indicates? When I have z1 of s of by 2ks by s square plus omega square, you can find out the value of k by applying the method of partial expansion, right? So the way in which how we will find out, that is 2ks is equal to s square plus omega square into z1 of s at s is equal to s square is equal to minus omega square, right? This way we can find out the value of k, or straight away if I want to value of k, I can divide this with 2s z of s. Okay, z of s. From that we will find out k is equal to s square plus omega square into z of s divided by 2s. At s square is equal to omega square, you can find out k. But how the elements are there in the z term? In previously we have shown removal of a constant, removal of a pole from infinity, nothing but inductor in series. If it was an admittance function, then capacitor in shunt. And removal of pole from origin, nothing but capacitor in series. Or if it is admittance function, then it is inductor in shunt. Okay. So I can write the order of denominator is greater than numerator, so I can inverse this, right? As we seen in the continued fraction expansion. I can write y1 of s is nothing but s square plus omega square divided by 2ks. So nothing but y1 is nothing but something in y2 plus y3 form. So which is nothing but y2 of s plus y3 of s form, and these are parallel to each other. So we end up with s by 2k plus omega square by 2ks. Omega square by 2ks. So what it indicates, what this term cs, correct? So c value is 1 by 2k. So in terms of z1 of s, we will write an inductor and a capacitor. It goes further, z2 of s. Inductor value is what? 2k by omega 1 square, 2k by omega square, 2k by omega square, and divided by omega square by 2k, so 2k by omega square, and c into s, so 1 by 2k. This is in farad, this is in Henry. So z1 of s is removed from z of s. Nothing but inductor and capacitor are in parallel and they are together in series with respect to the overall circuit. So removal of a conjugate imaginary poles, nothing but removal of L and C, which are in parallel, right? And they are kept in series with the rest of the circuit. What if instead of z of s, I had y of s, nothing but p of s by square plus omega square into q1 of s. if I had this as an admittance function, then this would have been my y1 of s. This would have been L into s plus capacitor. So the other case, if I would have had this as y of s, this as y of s, it goes further, this will become y2 of s, right? And this will also become y2 of s. So this one y of s, y2 of s, we end up this one as y1 of s, y1 of s. This will be my z1 of s, z1 of s equal to this. So I can write this one into z1, z2 and z3, correct? So when I have z2 is nothing but this, so nothing but L into s. So inductor will be having 1 by 2k Henry and capacitor will be having 1 by Cs. So 2k by omega square. So what happens in the next case, we have y1 in parallel to y2. So we have inductor and capacitor, and this will be y2. Inductor and capacitor, and this will be, and the value of, I will represent L1 C1. I don't want to confuse you with this. So L1 is 1 by 2k Henry and C is 2k by omega square. So if you see, the values are interchanged. Capacitor becomes inductor, inductor value becomes capacitor in shunt. So given a function which is y of s, then we can remove a conjugate imaginary poles by this fashion. We can do the k equation from this, nothing but s square plus omega square y of s divided by 2s at s square is equal to omega square. If there are more number of conjugate poles, it is square plus omega 1 square into s square plus omega 2 square into s square plus omega 3 square. We would have had, if it is z term, then LC parallel, LC parallel, LC parallel goes on. That will be equivalent to Foster form 1. And if it would have been, question would have been y of s, then LC parallel, LC in series but again parallel cascade kind of thing. So that would have been Foster form 2. We will see those in the next, where in which we will discuss more about Foster form 1 and 2. So the last one left out is removal of constant. So coming to the removal of constant, a given z of s can be written as some constant times of z2 of s. My constant is my z1 of s. Okay, given any in partial fraction expansion or conjugate fraction expansion, we can remove the first. Like maybe the z of s is in the form of a0 plus a1 of s, a2 of s square, so on, and we have in the denominator b0 plus b1 of s, so on. So a0 by b0 can be taken out, the first. So there is no s term, right? So k is the constant. So I can write that k as then resistance, which is k ohms, and we have a z2 of s. This is a single port. Okay, removal of a constant from the equation. So z of s will not be having this constant k when compared to z. So if the given equation itself is y of s, then I can write some k dash. Consider k dash. I don't want to confuse you with this k. So k dash plus y2 of s. K dash plus y2 of s. What is k? K dash is nothing but a conductance with the value k dash, which is in parallel with the rest of the network, which is y2 of s, right? So this way we can represent k ohms, k dash Siemens or more in parallel to y2 of s. So this is pretty easy. So we need to remember, given an equation, if you want to realize a network, then we will find out whether a pole lies at infinity or pole lies at origin, or is there any complex conjugate poles in the equation, that is the denominator equation. Okay, and we can remove a constant from them. So the moment you keep on removing, the network will keep on building. Okay, so Let's go for the problems where we can see. We will do some general problems, then we will see if we can build it for our Foster form 1, 2, chord form 1, 2. So for removal of pole from infinity, removal of pole from infinity, let's take z of s is equal to s to the power 4 10 square plus 7 plus 2s, s to the power 4 plus 10 square plus 7 s cube plus 2s. So from this given function is a impedance function, so we will be having z1 plus z2 plus z3 so on, right? So I can see from this given equation that maybe one pole is lying at origin, but numerator has 1 degree greater than that of the denominator. So one pole has to come from infinity. That's the priority. One pole has to come from infinity. So we will be having series inductor, right? By inspection only. So my something will be of the order ls plus z2 of s, right? So how to do this? Let's go for the continued Braixen expansion, which we have seen in the Hybris polynomial. So we will divide by s cube plus 2s, 10 square plus 7. So when we have s is equal to, multiplied with this, s to the power 4 plus 8s square, sorry, 2s square. So we end up with 8s square plus 7, right? We have to divide this from this. S cube plus 2s. This is continued Braixen expansion I am doing. 8s square. So s by 8. So s cube plus 7s by 8. What we have this? 7 2s minus, first one is 0, plus 9 s by 8 okay. So we have to divide this thing again, 8 square plus 7. So we need to have 64 by 9. 64 by 9, when I multiply with this, we will have 8 square. 64 by 9. So we end up with 7, 9 by 8s, right? 9 by 8. So we have to have 9 by 56, yes. So 9 by 8 is we end up with 0, right? So this way we can do a continued Braixen expansion. So the first term obviously is L into S, which is nothing but straight away S. Then we will have next term Z of S, nothing but 8s square plus 7 divided by s cube plus 2s, right? 8 square plus 7, the remainder divided by divisor. So this denominator has 1 degree greater than that of the numerator, so we went further on continued Braixen expansion. So we end up with s plus 1 by this we made into. So z next becomes y. This is z. This is z1, this is z2. It becomes 1 by y2. So here this is representing the z term. Whatever we do, this is representing a y term. That is s by 8 is the y. This is y. Plus 1 by comes into picture, then this will be a z term. Okay. This is a z term. The last one will be a y term. So 1 by z term, so 64 by 9 s plus 1 by 9 by 56 s. Okay, 64 by 9s. So this is representing z, y, z, y. So I can recollect or realize a network in the way L into S, right? The value, first one is 1 Henry. Then Z2 of S, right? Z2 of S in this form. But Z2 has got this capacitor, correct? Capacitor 1/8 farad. The first one is inductor LS, CS, LS, CS, because of Y term. See. So the next term, Y parallel to this, parallel in the sense, again comes into series. So 64/9 Henry, correct? Then the last element will be capacitor 9/56, 9/56 farad, 9/56 farad. This is the way we can realize a network. Here we went ahead for the explanation of removal of a pole from infinity. That means the numerator has 1 degree greater than that of the denominator. So we started on removing the higher order S terms. And this first element is Z, then next will be Y, next will be Z, then next will be Y, and goes on. And here we end up with LC, 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 LC. So this is the ladder structure, which is LC. This will be definitely a car form 1. But this is the problem when we can remove a pole from infinity. Let's take a removal of pole from origin. Remove a pole from origin. So let's consider Z of S is nothing but S square plus 4S plus 40 divided by S into S plus. So from the polynomials, numerator and denominator, we see that both are of same order. But there is one pole lying at origin. S is equal to 0. Correct? One pole lying at origin, another pole at minus 10 G omega S plane. So we have to remove a pole from origin. How we do? We write this in the reverse order. Better we write this in the reverse order. 40 plus 4S plus S square divided by 10S plus S square. 10S plus S square. And we go again further for continued fraction expansion. So that is 10S plus S square, 40 plus 4S plus S square. So when we can get 40, when we have 4 by S, right? We have 4 by S, we can get 40. 40 plus 4S, right? Straight away, both of these get cancelled, S square. S square, then again, further you go for removal of other lower order S terms. So 10S, 10 by S. 10 by S is 10S, so S square. So S square, when we have A1, S square, 0. Fine. So the first term means for Z, obviously the second term meant for Y, the third term meant for Z. Okay. So we end up with, first is Z, so 4 by S. 4 by S means remember a capacitor, that is 1 by CS. C will be having 1 by 4 farad. 1 by 4 farad. 1 by CS, so C is 1 by 4 farad. The next, it is Y. Y is nothing but a parallel. So parallel, what is that? 10 by S. 10 by S means it is having an inductor, right? 1 by LS. Y is there, 1 by LS. So it is 1 by 10 Henry. The third again in series, but Z is equal to 1 indicates 1 ohm. 1 ohm. This is the complete network which we have relied. Yes, coming to the removal of complex conjugate poles, let's take an example. Let's consider, instead of Z of S, let's take Y of S. Nothing but S square plus 2 divided by S square plus 1 into S square plus 3. Here we have two conjugate poles. That is S square plus 1 giving you a conjugate pole, one set. Another S square plus 3 will be giving you plus plus or minus j root 3, right? Plus or minus j, so which is lying on the j omega axis, and we know that residue of that is to be positive and real. So we can write this one as k1 by s plus j1, k1 conjugate s minus j1, and the other part, this is partial fraction expansion. So k2 by s plus j root 3 plus k2 star s minus j root 3, right? And we know that as it is a PR function, k1 and k1 star has to be constant k1, right? k1 and k1 star is equal to same and has to be positive and real, and as well as k2 star is nothing but k2 only, right? Then we can write this equation, that is y of s. Y of s can be written as 2k1s by s square plus 1 2k2s by s square plus 3. Please recall the previous session we have seen in the conjugate poles, the removal of conjugate poles, we end up with 2k1s, that is k1 and k1 are same, k1 and k1 are same, then k1 into s plus k1 into s will be added to k1s, whereas k1 into minus j1 and k1 into plus j1 will get cancelled, so we will have 2k1s by s square plus 1 s square plus 3 will be having 2k2s, and we need to find out what is the value of k1 and k2. k1 is nothing but s square plus 1 into multiplied by y of s divided by 2s, right? At s square is equal to minus 1. And k2 is nothing but s square plus 3 multiplied by y of s divided by 2s, 2k2s. And s square is equal to minus 3. Let's put all those values and let us see what will be the result. S square plus 1 divided by 2s, and y of s is this, which is nothing but s into s square plus 2 divided by s square plus 1 s square plus 3. This is and this s goes, at s square is equal to minus 1. So this s square as this goes. So we end up with minus 1 square plus 2 is 3. 3 divided by 2 into, minus 1. Minus 1 plus 2 is 1. 1 divided by 2 into minus 1 plus 3 is 2. So is it 1 by 4? We get k1 is equal to 1 by 4. So next, when we take out from s square is equal to minus 3. So s square plus 3 into divided by 2s into y of s. Y of s is this. So s into s square plus 2 divided by s square plus 1 into s square plus 3. When s square is equal to minus 3. So this get cancelled, s term get cancelled, keep minus 3. Minus 3 plus 2 is minus 1. Minus 1 divided by 2 into, this 2 into minus 3 plus 1 is minus 2. So is it minus 1 by minus 4? So minus minus get cancel, 1 by 4. So I will rub this part and we end up with k1 and k2 is equal to 1 by 4. So I can tell k1 is equal to 1 by 4. Y of s becomes 1 by 4 into 2s is but s by 2, s square plus 1 plus s by 2, s square plus 3. Right? This is the expansion, partial fraction expansion of the given y of s. And we know that this y is nothing but two functions. So which is nothing but, let me take y1 is this, y1 of s, and this is y2 of s. So I can write both of them in parallel, right? This one will be y1 and this one will be y2 of s. This way our circuit synthesis will happen. And as we know, y1 of s is nothing but s by 2 divided by s square plus 1. y1 denominator will be more greater than that of the numerator, so I can make it convert into z1. z1 of s is nothing but s square plus 1 divided by s by 2. So we have s square divided by s by 2 is nothing but 2s plus 2 by s, right? So we have z, which is nothing but z2 plus z3. z2 of s, z3 of s. What it indicates? This indicates L into s, right? When it is a z, it is L into s, that is 2 Henry. And when it is z, then it will be 1 by cs. So it is nothing but 1 by 2 farad. Correct? So y1 of s can be replaced with this. That is, we have an inductor and a capacitor. Inductor value is 2 Henry and capacitor value is 1 by 2 farad. Okay, 2 Henry, 1 by 2 farad. The next we will see what is that element leads to. Y2 of s. So I can write this thing as Z2 of s. Z2, Z3 is there, then Z4 of s. Let me take Z4 of s. Nothing but s square plus 3 divided by s by 2. Correct? So I can write s square by s by 2 is nothing but 2s plus 3 by s by 2 is nothing but 6 by s. So it has got z5 plus z6. z5 is nothing but L into s, that is 2 Henry is the inductor, and 1 by cs nothing but 1 by 6 farad is the capacitor. So I can write here it is nothing but inductor and capacitor in series. These are series, but inside this y2. So inductor is 2 Henry, capacitor is 1 by 6 farad. So this way we can remove a complex conjugate poles. Fine. So once we know from the given equation how to find out how to remove a pole from infinity, that is removing higher order s terms, removal of a pole from origin, that is a removal of lower s terms, then removal of conjugate poles, then nothing but a partial fraction expansion. You need to make sure that k1 and k2 has to be same, k2 and k2 star has to be same. This way you can, many number of problems you can have, 2, 3, you can keep on adding the elements, you can still deduce the network which will be LC, LC, LC. Series LC, but they are in a ladder structure parallel to each other if it is given function is y of s. If the function is z of s, the same function if I take it as z of s, then what would I have got? What would I have got? Inductor, or let's take the same problem. Let's take the same problem considering this as a z of s. So let's take the same problem and we'll see what will happen. So if I have the same problem, z of s is equal to s into s square plus 2 divided by s square plus 1, and we need to synthesize the network, we have to remove complex conjugate poles. Everything goes same, 2k1s by s square plus 1, 2k2s by s square plus 3, and we know that k1, k2 will be 1 by 4 itself, what we have seen in the previous problem, the same problem, but right now here it is z of s. So once we go further for solution, z of s is nothing but s by 2 s square plus 1, s by 2 s square plus 3. Now this z is nothing but z1 plus z2. Okay, z1 plus z2. This is z1 and this is z2. Right? This is the way we can synthesize. z1 and z2 are in series, but we don't know what are the elements lying. Definitely, as it is complex, we will be having L and C parallel. So z1 can be written, this z1 and this z2 can be written. z1 can be written as y1, which is nothing but s square plus 1 divided by s by 2, nothing but we have 2s plus 2 by s, right? So this is y3 and y4, y3 and y4. So as y3 says that this is nothing but c into s, right? Y term in the admittance. So c is 2 farad, and here it is L is inductor 1 by 2 Henry. So the first term is replaced with, if I write the elements, first will be capacitor and inductor. You can interchange this, no problem, but the value has to be taken care. So if I write here in capacitor, then it has to be 2 farad, correct? So this will be 1 by 200. You can interchange, write it whichever way you want, but make sure that you end proper results. The next one, Z2. Z2 can be written as, let me consider Wi-Fi, that is S square plus 3 divided by S by 2, nothing but Y6, Y7. So 2S plus 6 by S, Y6, Y7, both are parallel, and one will be in capacitor and another will be an inductor. Okay. So the capacitor value is 2 farad, inductor value is 1 by 6 Henry. So you could have seen that LC in series combinations, okay, LC together are parallel but series elements will be representing for the Foster form 1, and the previous what we have seen for the Foster form 2. Foster form 1 is meant for the impedance function, Foster form 2 is meant for the admittance functions, right? And core form 1 and core form 2 are there, which is straight away found out from control Braixen expansion.